moment. And this example we had actually, it was already solved in earlier classes, so was not discussed in much detail. I'm not having any plans to discuss it again further. So basically, if you have any fixed beam, and you have a distributed load like this, we all know that the end moments Asadullah Khan, he's trying to enter using outside IT login ID. Okay. So there will be end moments acting like this, and these moment values will be, if this force is W, distributed load is W, length is L, then this moment will be W L square divided by 12. Right? This we had discussed before, and that's what we will use. If it is a concentrated load of E, then the moments will be again in the same direction, and they will be equal to PL divided by 8. Correct? So there is a table like this available. This is the PL by 8, and this is WL square by 12. Likewise, many other combinations can be possible. You can have 3 loads acting at equal, 2 loads acting at 3 equal intervals. Then the moment values are available. You may have uniformly distributed load acting up to half a distance, or a triangular kind of a linearly varying load acting, and then again the moment values are available. So you can feel free to use this table, but for basic ones such as this P and W, one should memorize what are the moment values at the end. This is not too much to memorize. Okay, so let's do an example today, and here we will get to see how to apply this concept. Okay, and as I had mentioned before, the fixed end moments that we were calculating, these are not really this term here. This is an effort to account for the forces that are acting along the length of the member. So for example, in this structure, if you see, there is this force, this P by L, this acting along both members. Member, if I can call it member 1, member 2, member 3, then this P by L, W is equal to P by L, is acting along 2 and 3. And then this PL moment, okay? There are 1, 2, 3, 4 types of forces. Out of these 4 forces, which of them can be accounted for by this vector? Let me call it force 1, force 2, force 3, force 4. Which of them can be brought into this vector? Can one be brought into this vector?
2 and 4, sir.
2 and 4, right? Yeah. So since 2 and 4 are acting at one of the degrees of freedom, okay, they can be brought in. But 1 and 3, they are acting along the length of the members. And I don't want to define another degree of freedom here. If I were willing to, then even 1 could be incorporated, but I don't want to do that. That will unnecessarily increase the size of my problem. I will unnecessarily add more degrees of freedom. Whereas on the other hand, I can handle it in a sleeker way. Okay, so that's what I'm trying here. So what we will do is we will keep this 2 and 4 can be brought in here. 2 and 4. However, 1 and 3, they are distributed forces in a way, right? So for this, we have developed this device wherein we take the negative effect of these forces, and that is called AF-FEM, okay, or AFEM. Just combine the two, AF and AR, and that you call AFEM. So AFEM is basically negative of the negative effect of the actual forces, and which forces that are acting along the length of the member. Okay, fine. So that is why when we put the left hand side of this equation, when we write this left hand side of this equation, we put a minus sign here. That minus sign basically represents that the AFEM that we are calculating, AFEM, that we are calculating is actually incorporating the opposite effect of the actual forces that are acting. Okay, fine. This I had explained in quite a bit of detail in the last class also, so I'll stop here now on that discussion. So we had all seen this equation, right? And I had told you that this is a very powerful equation. Last time when we wrote this equation, we did not probably write this term, but as I had discussed, this equation is nothing but A equals to SB, correct? And then A we had split into AF and AR, S as SFF, what is this one, and DS, DF and DR. Okay, this change we had done. Then subsequently we saw that, okay, when the forces are acting along the length of the member, then it is not simply A, it is A minus AFEM. Okay. Then both of these terms, A and AFEM, they can be broken into AF and AR. So AF, AR minus AF, FEM, AR, FEM. Okay, that's what. So this equation is obvious now, right? This equation should not give any surprises to you. This is, the rest of it is same. Fine. So this is what the equation we have. Now, if we were to follow the procedure that we had followed before, ideally what we should do is we should identify all the degrees of freedom. So fixed as well as free as well as restraint. So how many degrees of freedom are there? 1, 2, let's say I'm calling them that, but I'm already giving 1 and 2 names to these rotational degrees of freedom at these 2 locations. So let's not use 1 and 2, let's start using from 3 onwards. 3 and 4 here. Okay, 3 corresponds to vertical movement and 4 corresponds to rotation, and no axial movement because these are all beam elements. I'm saying that I'm ignoring the axial deformations. Fine. So 3 and 4 here. Then 5 here. 1 is already there, rotational. So 5 and 1. Okay. Then this one, I'll call it 6. So 6 is vertical movement, comma 2 is rotation. Okay. And then 7, 8. So total degrees of freedom of this system will be 8. Agreed? The first member would have degrees of freedom of 3, 4, 1, 5, 3, 4, 5, 1. The second one would have 5, 1, 6, 2. The third one would have 6, 2, 7, 8. Okay. Then what we should do is we should write the stiffness matrix for the first member. So ideally there are 3 members, right? 1 member, second member, third member, and the degrees of freedom corresponding to them are 3, 4, 5, 1, 6, 2, 7, 8. You can see that some jumbling has happened because I had picked 1 and 2 as I had called already these rotational degrees of freedom as 1 here, 1 and 2 here. So that's why I'm not using 1, 2, 3, 4, 5, 6, 7, 8 from one side to another. I'm using this order. Fine. Now, ideally what I should do is I should write the stiffness matrix, that is 3, 4, 5, 1, 3, 4, 5, 1. This kind of a stiffness matrix for first member. Likewise, then I should write another stiffness matrix for the second member. And then I should write the stiffness matrix for the third member. Right? So the second member would be 5, 1, 6, 2. The terms corresponding to 5, 1, 6, 2. The terms will be all the 12 EI by L cube, etc. Right? You are familiar with all those terms. 6 EI by L square, 4 EI by L, all those terms. 6 EI by L square and so on. So all those terms will be here. I'm not writing those terms, and ideally this is what I should do if I were just going with the brute force method. 5, 1, 6, 2. Then here will be the terms of 6, 2, 7, 8 and 6, 2, 7, 8. Right? And then these will be the terms that are overlapping, and that's how I'll get the overall stiffness matrix, which will be an 8 by 8 matrix. Then after developing this stiffness matrix, I will also at the same time develop an A matrix, right? Not AF, A matrix. And I will also develop a D matrix. Okay, and this will be actually not just A minus AFEM, which will also be 8 term matrix, and this will also be 8 vector matrix, right? Then after doing all this, we should move the terms of terms corresponding to first and second degrees of freedom up. That's what we did, right? So we moved the terms of free degrees of freedom one side and the degrees of freedom that are restrained to one side. Okay, so all those terms were moved up, all those terms were moved up, free degrees of freedom terms were moved up. And when we do that, from there, what we got at the end was AF, that is free degrees of freedom. And here it also takes AF FEM, okay, was equal to SFF, SFF DF plus SFR DR. Isn't it? This would have been the matrix equation. That is basically your first equation here. AF minus AF FEM is equal to SFF DF plus SFR DR. Okay. Now in this particular case, there are no non-zero boundary conditions. Okay, all the boundary conditions are given as zeros. That means my DR is basically 0. If the DR is 0, then my equation is reduced to AF minus AF FEM, this term minus this term, is equal to SFF DF, correct? And the DR terms are 0. So this is basically the equation that I need to solve. That is my first equation. So now, instead of going through all that procedure of developing an 8x8 matrix, and ultimately we have to solve only for this equation. And in this equation, what is the degrees of freedom I have to handle? SFF, what is the size of SFF here? What is the size of SFF? Anybody?
2 by 2.
2 by 2, right? Because these are the only 2 degrees of freedom which are free. The rest of it is all restrained. Okay, so it's only 2 by 2 equation that I need to solve. Right? This matrix is only 2 by 2, so there will be 2 equations, 2 unknowns that I need to solve. Why should I write that 8 by 8 matrix if I can somehow avoid that? So that is where we will discuss. So I'm just kind of taking a shortcut here just to make it easier. Okay. Then you typically use the computer program. It is very difficult to change the computer program in such a way so that you do only these separately. So typically we write the full global matrix and then solve it. But anyway, since we are doing by hand, it's much easier. So here we can look at each and every term. AF corresponds to what are the forces acting at the free degrees of freedom. So in direction 1 and in direction 2, what are the forces acting? In direction 1, what direction 1 is the rotation at this location. Is there any force acting in this direction? No. There is only vertical downward force acting, but that is not degree of freedom 1. That is a different degree of freedom. So that value is 0. The force acting in the second degree of freedom here, second free degree of freedom, is PL, but in the clockwise direction. And my second degree of freedom is in the anti-clockwise direction, positive. So I'll write it as minus PL. So my AF is sorted, right? AF is resolved. The issue is now AF FEM. AF FEM basically is in these two. If I had this member, let me erase this again, just to reduce the clutter. Let me take a blue color so that it will be. So you had this member, this end was fixed, then you have a roller support here, you have another roller support here, then this end is also fixed. Now, AF FEM basically means is that if I fix these 2 boundary conditions also, these 2 freedoms also, degrees of freedom also, if I restrain them, then there are forces acting like 1 and 3, this and this. For these forces, that is this force and this force. This is P and this is P by L. So for these 2 forces, what will be the moments acting at this location and this location? That's what I have to find out. Okay. That is what my AF FEM is, because I'm talking about AF, right? So AF corresponds to only these 2 degrees of freedom, rotation here and rotation here. That is moment here and moment here. Okay. And because of this P and this PL, that's what I have to do. So let's go step by step. I'm sure all of you can calculate it, but I'm just following it. In online method, it's very difficult to know whether you know it or not, because I cannot see your faces. So I would anyway complete the process. So we know the fixed end moments for this kind of a case, for this member would be at this location. What will be the fixed end moment? If I am applying a load P here, the moment here will be
PL by 8.
PL by 8. Correct. Very good. And for this member, the length is 1.5 L. This member, the length is 1.5 L. You have to be mindful of that. And then there is a W of P by L acting. Okay. So the moment that I have to apply on this side, on this member, is how much? W L square by 12, right? So W will change it to P by L into L square. L square will become 2.25, or if I'm using fraction terms, then I will use 3 by 2, right? So 9 by 4 L square, right? Square of WL square by 2. Okay. So this is what it will be, 3, 4. So it is basically 3 by 16 PL. Is that correct? 3 by 16 PL. Fine. Everybody agrees? 3 by 16 PL?
Yes, sir.
Yeah. So now you can see that the two are in opposite directions. So PL by 8 is in the clockwise direction. So I'll write that as negative. And 3 by 16 is in the anti-clockwise direction. I'll write that as positive. So basically this support has to be providing this much of external moment, which is basically balance of this and this. Okay. If these two moments are balancing each other completely, then this value would have been 0 even. That would have been okay. But they are not balancing each other. So this much of external moment has to be supplied here to balance it. Okay. To keep it from rotating. Okay. Similar thing here. So for this end now, what we are looking at, let's see. Now I'm looking at member 2 and member 3, this member and this member. So let me create a gap here. Slight gap. Member 2 and member 3. This is member 2, this is member 3. Now, of course, W that is equal to P by L is acting in both of them, or on both of them. This length is, the length of this member is 1.5 L. Okay. So what will be the moment demand here? The moment demand will be, or the fixed end moment will be WL square by 12 again. So that we had calculated just now, that will be the same. We had calculated to be 3 by 16 PL, isn't it?
Yes, sir.
Yeah. And the moment here will be WL square by 12. So W is P by L into L square divided by 12. So that is PL by 12. Okay. Again, they are in opposite directions. This is in clockwise direction and this one is anti-clockwise direction. So we have to take the difference of the two. So 1 by 12 minus 3 by 16. That's correct, because this is anti-clockwise, right? So this is positive. 1 by 12 minus 3 by 16 is how much?
5 by
48. Yeah. 4 minus 9 minus 5 by 48. That's what it is. Okay. Everybody is clear with that?
Yes, sir.
Anybody has a doubt? Any questions about this one? How we got these values here? These two values. Fine. So we got AF. We got AF FEM. All we have to do is we have to subtract the two, AF minus AF FEM. That will give us the A vector. That is left hand side of this equation. Okay. The right hand side of this equation is SFF DF. Now DF of course is unknown, right? By definition, DF is unknown. That's why we are calling them as free degrees of freedom. We have to calculate the displacements there. What we know, however, is SFF. So SFF is basically the stiffness matrix corresponding to 1 and 2 degrees of freedom only. Okay. And let's take a look here. Now, what I'm saying is basically SFF will have 4 terms: S11, S12, S21, S22. Okay. And what does that S11 mean? S11 means if I rotate this joint by a unit rotation, how much moment I have to apply at this same location. S12 basically means is that if I rotate 2 by unit, how much moment will I have to apply here? Okay. And likewise, S21 basically means if I rotate this joint by 1 radian, how much moment I have to apply at 2. And S22 basically means is that if I rotate 2 by unit, how much moment do I have to apply here at second degree of freedom? Okay, so we will go one by one. S11. S11 is nothing but if I'm rotating this joint by 1 radian, what does that mean? It means that, let me draw it here itself. If I'm rotating it in anti-clockwise direction, this will deform this way. And then every other degree of freedom is fixed, right? So its location cannot shift. Joint 1's location cannot shift. And joint 2, this joint here, this joint's location or rotation cannot change. So it remains perfectly horizontal. Okay. Likewise here. Got it? This is not perfect. Okay, it's not a perfect drawing, but I hope you understand. Fine. So it is causing a rotation here, and it will be requiring a moment demand here and a moment demand here also. But right now for S11, we are interested in knowing how much moment will be required here. So we can go back to our stiffness matrix terms. And if you remember already, ideally you should remember it because you have all been doing this moment distribution method during your BTech. So this was the stiffness matrix. This was the stiffness matrix for a plane beam. Okay. So you remember this term here, 2, 2. Right? So if you rotate in this beam, if you rotate this joint by a unit, so how much moment did you have to apply? You have to apply 4EI by L moment here. And how much moment did you have to apply here? This moment was also in anti-clockwise direction. How much was it?
2EI by L.
2E by L.
Yeah. So this is all very regularly used in moment distribution method. That is the carryover factor. So carryover factor is always half, right? That is what 4 divided by 2 or 2 divided by 4. That is your carryover factor. Okay, so so we know that, and so we have to remember that if we are producing a unit rotation here, at the other end we will still be requiring a moment of 2EI by L. Okay, coming back to our problem now. So here 4EI by L will be required because that will be the moment resisted by this member, that is 4EI by L, because the length was L, and similar moment will be resisted by the other member. However, in that case the length is 1.5 L. Okay, so 4EI by L resisted by this member and 4EI by L resisted by this member. The total stiffness for this degree of freedom will be summation of the two, that is 20EI by 3L. And you can see that if you develop the full global matrix, you will see that you will end up with the same value. Okay, essentially what you are saying is when you are rotating this joint, when you are rotating this particular joint, you are making both members bend. Okay, so both members are going to offer the resistance, and that is this resistance, summation of the two resistances. Okay, fine. Moving forward, S12. S12 is basically when I am rotating this about second degree of freedom, when I am rotating this joint that is in the second degree of freedom by a unit, that is, this is going up like this and this is going down like this. Okay, how much moment do I have to apply here? Okay, so as we remember, the carryover factor was half, that is 2EI by L has to be resisted on this one. Okay, and this L will be this time 1.5. Okay, and this is rotating in this direction, the moment has to be applied in the anti-clockwise direction. So that is 2EI by 1.5 L, that is 4 by 3 EI by L. S21 will be exactly the same. In this particular case, we are rotating 1 by a unit and observing how much moment I have to apply here to not allow it to rotate. That is same, 4EI by 3L. Okay, and that is also because the matrix is symmetric. Right? S22, again, very similar to what we had done in case of S11. We are rotating this second degree of freedom. We are creating a unit deformation in the second degree of freedom. So that means we are pushing it up this way, we are pushing it down this way, right? So you will have 4EI by L term coming out of this side of resistance and 4EI by 1.5 L will be coming from this side of resistance. So that is again equal to 20 EI by 3L. Okay. So we can very quickly calculate the stiffness matrix or SFF part of the stiffness matrix, because that is what we are primarily interested in at this time, without having to handle that 8 by 8 matrix. But that will only give me the rotations at the 3 degrees of freedom. If I want to calculate reaction forces, for example, how much is the moment, how much is the reaction here, how much is the moment here, then again I have to calculate other parts of the stiffness matrices. Then eventually you have to calculate all those terms, but at least for the hand calculation, it makes life much easier. Okay, if I'm only interested in calculating the DF values. Okay, so this is my SFF matrix, which has terms of S11, S12, S21, S22. Okay, I've just assembled these 4 terms here. They are all assembled here. This is my SFF matrix. You can see it, right? Any questions so far? Okay, so now writing the equation back again, AF minus AF FEM is equal to SFF DF. I've got AF, which I had solved, AF minus AF FEM, I had solved it here. So that part. I've written that those values here is equal to SFF, this is this matrix, multiplied by DF, which is nothing but D1 and D2. Okay, now we got 2 equations, 2 unknowns to solve. You can solve it. You know how to calculate the inverse of a matrix, 2 by 2 matrix. That's pretty easy to do. So either way you can do it, and you can solve for D1 and D2. I've solved it for you. These are the values of D1 and D2. So these are the deformations or rotations in these degrees of freedom 1 and 2. What are the rotations here? Okay, so this much you can do with just the calculation of SFF. You may have to calculate the SRF also if you need to calculate what are the reactions. Okay, but anyway, that is not really the objective of this part, so I'm skipping that part. Fine. So now we know how to handle the forces that are acting along the length of the member also. How to incorporate that in the matrix method of analysis. Any questions? Please, somebody should ask some questions at least. I'm getting a feeling that nobody is following me, what I'm saying. No? Okay. So moving forward. So now the next portion of this chapter is basically, so far whatever we have discussed is only in the context of a beam elements, right? So we have been dealing only with plain beam elements, and each node we had only 2 degrees of freedom for a beam, right? We had only allowed the lateral movement in one direction, not even in the other direction. That would have been a space beam, but we have allowed only plane beams, only this movement of the beam end, and then rotation. Okay, and rotation also in this plane only. So there is this plane. In this plane, it can rotate. Each joint can rotate in this plane, and it can move vertically in this plane. Okay, not even horizontally in this plane, because that is axial deformations we have ignored. So one way to approach, or one way to evolve from here could be, so we have handled plane beam problem. Why don't we go into a plane frame problem, which will allow axial movement also? Then we can go into a space beam problem, which will allow lateral movement in out of plane direction. And then we can go into space frame problem, and we can go into space truss problem. But what I was thinking is that what I prefer to do is that instead of dealing with a beam problem and slowly evolving, let's jump into the most generic case now. What is the most generic case from a plane beam, which incorporates all possible degrees of freedom? Which one would be the most generic case?
Frame. So
Frame. Plane frame?
Space frame, sir.
Sorry?
space.
Space frame.
Space frame, yes. So space frame basically, if I talk about a space frame, I mean, this is the slide I had opened already. So In a space frame, you allow all 6 degrees of freedom at each joint. So you have these 2 joints. At each joint, we allow 3 movements. Which are the 3 movements? Axial movement, movement in one of the lateral directions, movement in another lateral direction. So 3 movements and 3 rotations. Which are the 3 rotations? The twisting rotation, okay, that is rotation about the axis of the member, okay, rotation in one of the planes and rotation in another plane. You followed me? So at each joint, we allow 6 degrees of freedom. So for example, for a plane beam that we were discussing so far, we had only 2 degrees of freedom at each joint, and we can expand it to up to 6 degrees of freedom. So let's all the important constituents of that space frame problem we have already discussed, and that's why I feel confident that we can move to space frame now. Okay, and I'm sure that you will be able to follow. Okay, so what we will do is we will try to develop the stiffness matrix of a space frame first. So I have a space frame member. What would be the stiffness matrix? So what would be the size of the stiffness matrix of a space frame member?
12 by 12.
12 by 12, right? Because you have got 6 degrees of freedom at each joint, right? So in a plane beam, you had 2 degrees of freedom at each joint. So your stiffness matrix was 2 for this one, 2 for this one, 4 by 4, correct? For a space frame, you got 6 here degrees of freedom. So you got 12 degrees of freedom, and therefore the stiffness matrix will be 12 by 12. Okay, so this is how I represent. This is how we represent a space frame member. Let me call it JK member. Okay, or member JK. Now in member JK, joint J has 6 degrees of freedom. 1, 2, 3, 4, 5, 6. Now what do 1, 2, 3 represent? What does 4, 5, 6 represent?
4, 5, 6 are movement, sir.
Translations.
Yes. Yes. So 1, 2, 3 that are in kind of a brown color, those represent translation degrees of freedoms, and 4, 5, 6 represent rotational degrees of freedom. Or if you're talking about forces, 1, 2, 3 represent forces, 4, 5, 6 represent moments. I'm sorry. 4, 5, and 6 represent moments. So can anybody tell me, out of these 6 degrees of freedom, which 2 were active when we were dealing with plane beam? In case of a plane beam, we had only 2 degrees of freedom at each joint.
2 and
Which 2 were?
2 and 4.
Very good. 2 and 4. It's not 2 and 4.
5 or 11.
5 and 11. You should notice that 5 is the rotational degree of freedom. And 11 is at joint K. I'm only talking about joint J for the time being. So at joint J, which there were 2 degrees of freedom in plane beam at that joint.
5 and 2, sir.
5 and 2. Are you sure?
2 and 6, sir.
2 and 6. Yes. Yeah. So 2 and 6. Somebody else had also answered before. I cannot see your. I mean, either I can see the presentation or I can see if, the Google Meet screen. So I cannot see the Google Meet screen right now. So I don't know who is answering what. But anyway, yeah, 2 and 6 is the correct answer. 2 is the translational degrees of freedom in the lateral direction. That's what was free. And 6 is the rotation. Okay. So 6 is associated with 2. Okay. Flexural deformation in this member, which produce the translation in second degree of freedom, also produce rotation in 6 degrees of freedom. So they are corresponding to each other. Likewise, 3 and 5 are corresponding to another type of flexure. Okay. So if you have this member, for example, you can see my hand, right? This arm, you can see. So on this one, at this joint, this is joint J. If I rotate it by this in this direction, okay, that means I'm getting this kind of a twisting, and also this twisting is corresponding to the movement in the vertical plane. So movement in the vertical plane is marked by degree of freedom 2, and this twisting is marked by degree of freedom 6. Or this, I'll call it twisting. It's not really this twisting, and what I mean is that this rotation. This rotation is marked by 6. Agreed? So 2 and 6 are corresponding to each other. Similarly, if this member is this way, now if I'm twisting it about 5, right, Which kind of deformation am I getting? Which kind of translational degree of freedom am I utilizing? 3 in out of the plane direction. 3 is in the out of the plane direction. So 5 and 3 are combined together. Okay. And 1 corresponds to what behavior?
Actually.
Axial
And 4 corresponds to what?
torsion.
Torsional. Right? Agreed. Very good. So 1 and 4, as far as we are dealing with this problem, there are several simplifications we are making. We are making simplifications such as 1 is not coupled with, so 2 and 6 are coupled. So when we produce a deformation in 2 direction, we also produce rotation in 6 direction. Likewise, 3 and 5 are coupled, or they are corresponding to each other. We cannot have 2 without 6. We cannot have 3 without 5. Okay. So when we produce 3, for example, we also produce 5. But our 1 degree of freedom, that is axial behavior, is completely independent of the rotational or the flexural behavior. That is, it does not get affected by any movement in the 2nd or 3rd or 5th or 6th degrees of freedom. Okay, that is a major assumption we are making, which may not always be true, but we are saying is that our AE by L properties, you know what is AE by L? AE by L, AE divided by L. A corresponds to the cross-section area.
Axial stiffness.
Axial stiffness of the member. So our axial stiffness of the member does not depend on what level of flexural deformations or what is happening in the flexure. Okay, that might be true in elastic range for most of the members as long as we are not accounting for any geometric nonlinearities, etc. But it sometimes can be questioned and challenged, and there will be limits to how far we can keep making that assumption. Okay, but for the discussion in this chapter, at least for the purpose of this discussion, we are assuming that our behavior in 1 degree of freedom is independent of the behavior in 2, 6 degrees of freedom and 3, 5 degrees of freedom. And similarly, the behavior in 2, 6 degrees of freedom, that is 2 and 6 combined, is also independent of the behavior in 3 and 5 degrees of freedom. Okay. What does that mean? Is that if I have, let's say, this beam again, and I'm bending it in this plane, that's whatever behavior I'm getting, it will not be affected by what level of bending I'm applying in this direction. Okay. And again, this remains true as long as material behaves mostly linearly and there is no geometric nonlinearity involved. That is true. But if we go into large deformations, geometric nonlinearity starts to play a role, then this gets questioned. Or if the material starts to behave nonlinearly, then this gets questioned. Okay. So we are not going into those domains yet. Then comes the question of 4th degree of freedom, which can be a whole course in itself. Okay. What is 4th degree of freedom? You just explained. Somebody just answered. It is torsional degrees of freedom, right? 4th and 10th. 4th for joint J and 10th on joint K. Okay, they are both torsional degrees of correspond to torsional degrees of freedom. So, how much torsional restraint would a member offer is a very for a unit rotation. Let's say. So, if I rotate the member in the 4th degree of freedom by a unit rotation, how much torsional restraint or how much moment will I have to apply? Okay. And that question is a very difficult question to answer and depends on so many different factors. Okay, that is okay up to if we don't include the effects of warping. If we include the effects of warping, then all this whatever discussions we are doing becomes very questionable, because warping is nothing but in a way kind of a bending. Okay, so I don't want to get into that. I hope those things have been discussed in bit of a detail in mechanics course. If they have not been, maybe some discussion might take place in stability course. If that is an elective we offer sometimes, where we cover some of that topics. But yeah, I mean, so understanding the warping behavior is again that can be at least one full chapter in itself. So what we are doing is we are simplifying it in many ways. What we are doing is we are saying 1st degree of freedom is fully independent, and it is given by this stiffness terms EA by L. So you apply unit force in this direction, or sorry, you introduce a unit displacement in this direction at J degree of freedom, that is unit displacement, and you have to apply EA by L force here, and you have to apply EA by L force here in opposite direction. That's why minus sign. Okay. Likewise, for the 4th degree of freedom, that is this twisting or torsion, we are introducing a coefficient called Ix, or torsional constant. You might be familiar with this term, torsional constant, which somehow, by some magic, it incorporates all possible torsional rigidities of the member. Okay, so I don't want to deal with that problem really seriously. I just want to simplify that issue. So we bring in some torsional constant, assuming that there is no warping issues and it's all behaving perfectly. There is no interaction between twisting and bending, or twisting and axial behavior and all that. So if you make all those assumptions, then you can simplify it as G times G basically is the term which basically means that you are incorporating pure torsion. You are not taking into account any other complications. G times Ix by L. Ix is the torsional constant divided by L. Okay, and this is your so this is the moment you have to apply if you want to turn this end by a unit, and opposite moment you have to apply at the other end. Fine. Now comes the question of second degree of freedom. So you cannot apply a unit movement in second degree of freedom without applying any moment in the sixth degree of freedom. Second and sixth are coupled, right? That we know from flexural problem. We have already solved a beam like that. So this is exactly what we had solved before. What is happening? You apply a unit displacement in the second degree of freedom, and then you get forces in second, sixth, eighth, and 12th degrees of freedom. So in the second degree of freedom, you get 12 EI by L cube. In the sixth, you get a moment of 6 EI by L square. In the eighth, you get a force of minus 12 EI by L cube. And in the 12th degree of freedom, you get a moment of 6 EI by L square. Okay, so these are the terms corresponding to unit deformation in second degree of freedom. Unit rotation in the sixth degree of freedom, is that no? It's a unit rotation in fifth degree of freedom that I'll hold for a mind. Unit rotation in the sixth degree of freedom. Again, we are familiar with these terms. These are 6 EI by L cube, 4 EI by L, 6 EI by L cube, 2 EI by L. We are familiar with these, right? So this is the beam, and we are rotating in the second degree of freedom. So we are rotating in the sixth degree of freedom. So this will be the deformed shape, right? This kind of a deformed shape. Similarly, we can incorporate the terms corresponding to, we have handled 1, 4, we have handled 2 and 6. Similarly, we can handle terms 3 and 5. This is 3 and this is 5. Okay, so if we introduce a unit deformation in the third degree of freedom, the terms will be very similar to what they would be if we introduce a unit deformation in the second degree of freedom. So the terms here and terms here will be very similar. You get 6 EI by L square, 12 EI by L cube. Only difference that is there between this and this is, what is the difference between these terms and these terms? You got 12 EI by L cube here, you got 12 EI by L cube here. The only difference was
in plane and
Plane, sir.
in which plane, right? So which cross-section value would you use? You would use Iz value here. Okay, that is the stiffness, or that is the moment of inertia for like in the z-axis. So if you take the neutral axis, which is in parallel to z-axis, then this will be the moment of inertia, Iz. Whereas here you would use Iy, wherein the neutral axis is parallel to the y-axis. Get it? Okay. Now, a couple of things you must remember. In all such cases, we always assume that x-axis is the axis that is connecting J to K. Okay. So that is the assumption that we start with. So we always orient our local x-axis, that is x member. So our member's x-axis is always going from J to K. It is not going from K to J. Whichever one you call J and whichever one you can call K. But once you decide this is the first one, this is the second one, J is the earlier number, K is the later number. So if you call it 1, 2, so X is always going from 1 to K. And that sign convention is important. We will see that in future. So X is always in that direction, and then Y and Z are parallel to the cross-section direction. So if you have an I section, for example, so between Y and Z, one of them will be parallel to the web, and one of them will be parallel to the flanges. And you can choose whichever one you want to be, but you have to maintain the this right-hand thumb rule or whatever, whichever rule you follow. So if you do that, so here, for example, if you see, here, for example, if you see 1, 2, 3, I'm following right-hand thumb rule, right? 1, 2, and 3. So the way they have to be associated is, in this particular case, my Iz corresponds to, let's say this is a, let me draw a little bit here. So this is the cross section, let's say, okay, and this is the axis which is parallel to this z axis, right? So this will become Iz. About this axis, if I calculate the moment of inertia, this will become Iz. However, if I calculate the moment of inertia about this axis, this will become Iy. Okay, so Iy is basically corresponding to the weaker axis, and Iz is the stronger axis, strong axis and weak axis, right? Because its Iz value is higher than Iy typically in an I section. So that depends on you. I mean, you could have called this one as Iy and this one as Iz. That's up to you. So in any case, whichever one you are calling Iy, accordingly, whichever one you are calling y and whichever one you are calling z, accordingly you will pick the values of Iy and Iz here. Fine. That is something that you have to be very careful about, which I to pick in which deformation. Fine. Any questions from here? Here Ix, basically when we are using Ix, we are not assuming it to be an I section, because if you are starting with an assumption of I section, you cannot avoid warping. Okay, so warping terms will not follow this kind of a stiffness terms. Warping terms are more complex. So for the purpose of torsion, we are assuming it to be a circular cross section. Okay, or we are ignoring the warping effects completely, okay, by some magic. Then you can come up with this kind of a simple terms for torsion. Fine. Any questions? All right. So the terms that we just saw, for example, here we had developed the stiffness terms, all stiffness terms in 1, 2, 3, 4, 5, 6, 7, 8 up to 12 degrees of freedom, but for unit deformations only in the first 6 degrees of freedom. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Only for 6 deformations we had developed the stiffness terms for all 12 degrees of freedom, which basically means that this is 1, 1, 1, 2, 1, 3, 6. So we had shown you the terms corresponding to this left hand side of this stiffness matrix, and similar terms can be developed placed on the other side also if you introduce unit deformations in the remaining 6 degrees of freedom. Okay, that is not a mystery. I'll not go into that. Right. So we had developed this term and we had shown you this term. Plus, accordingly, similar terms can be placed on the other side. Right. Does anybody have a problem with how these terms came about? You have to introduce only unit deformations in 7, 8, 9, 10, 11, 12. And accordingly, you have to populate the terms corresponding to all 12 force degrees of freedom. Okay. So this is how you can develop the 12 by 12 stiffness matrix for a space frame member. Right. If you look at the axial behavior, you got this one, you got this one, you got this one, and you got this one. So if you had a member which is only moving in the axial direction, your stiffness matrix will be only, stiffness matrix of the entire member will be only 2 by 2, and which will have these terms. Right? Fine. Does that sound okay? Does that look okay? Look at the rotational terms also. Go ahead. Somebody has a question? These are the axial behavior. These are the axial terms which are uncoupled. So if you see, if you go along this length, go along this row, you will see with 1 there is only one coupling, that is with 7. So 1 corresponds to axial movement in J, 7 corresponds to axial movement in K. Okay. So 1 has no coupling. So all the other terms are all 0. So if you introduce a unit deformation in 1, you will get a force at 1 and you will get a force at 7. And you will not get any other force at any other degree of freedom. That means 1 is completely, axial behavior is completely decoupled from all other degrees of freedom. Similarly, if you look at the torsional behavior, you apply a unit deformation at 4, you will only get a force requirement or a moment requirement at 4, and you will get some moment requirement at 10. And there is no other non-zero term along this whole thing. Likewise here, all are 0 except 4 and 10. This is 10. Right? So which again stands for, or which again means that 4 or the torsional behavior is completely decoupled or uncoupled from all other degrees of freedom. Torsional is purely taken care of by torsion only. Similar, but if you look at 2, then you will see that there is some interaction with other terms. Look at the degree of freedom 2. You will have terms of 2. So of course, you want to reduce the unit deformation in 2, you have to apply some force in 2. That's why this term has to be non-zero. Plus also you have relationship with 6. That means 2 and 6 are coupled. Then 8 and then 12. So you want to introduce a unit deformation in 2, you have to apply a force in this direction, you have to apply a moment in this direction, you have to apply a force in this direction, positive or negative, and you have to apply a moment in this direction. So that's why you have 8 and 12. This is 12. And this is basically 6. Right? So that's why you have coupling terms at 6, 8, and 12. Okay? I hope all this, how this stiffness matrix came about is clear to everyone. Now, of course, you don't have to memorize the terms of this stiffness matrix, but if you use this matrix frequently enough, you would start to memorize some of the terms. Okay? Now, moving forward, there are a few other features. So one thing we discussed, like for example, you can identify torsional behavior here, separate the torsional behavior from axial behavior, from flexure in one plane. So 2 and 6 is flexure in which plane? You can call it plane 1, 2. So flexure in plane 1, 2 is given by degrees of freedom 2 and 6. Similarly, flexure in plane 1 and 3. This is 1, this is 3. So flexure in plane 1, 3 will be given by deformations in 3 and 5.
5.
Okay. Likewise, we can also see the terms that are corresponding to JJ, joint JJ. So this is all 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So these are all coupling forces and displacements at joint J. These terms here are coupling the forces and displacements at joint K. These two parts or submatrices are coupling forces at joint J with displacements at joint K, or vice versa. Okay, so this is coupling displacements at joint K with forces at joint J. This one is coupling displacements at joint J with forces at joint K. What does M correspond here? It is for a member, right? So space frame member stiffness matrix. So this is the member stiffness matrix in member coordinate system. Why am I calling it a member coordinate system? Because my X, or my 1 degree of freedom, that is my X degree of freedom, that is aligned in the direction of J and K. Okay, that's why this is member coordinate system, and this is the stiffness matrix for the member. Okay, is that clear to everyone? Now, again, I can take, this is where we had started the discussion from. So if we take the subset of 2, 6, 8, 12 from here, 2, 6, 8, 12, and all the corresponding degrees of freedom, so, or all the coupled, so 2, 2, 2, 6, 2, 8, 2, 12, those terms, plus then you can go with 6, so 2, 6, 6, 6, right? Or sorry, 6, 2, 6, 2, 6, 6, and so on. So likewise, you can pick up those terms here, and you can see that all such coupling terms are marked here. Which terms do they, which are these 2 degrees of freedom, 2 and 6, or 2, 6, 8, 12? What do they correspond to? What type of member do they correspond to? 2, 6, 8, 12. If I pick these 4.
Plane beams.
Plane beams.
Yes, yes. Plane, not a plane frame, plane beam. Okay. When I am saying beam here, I mean plane beam. That is an omission from my side. Okay. So this is the stiffness matrix you will get. You have already used this stiffness matrix in 2, 3 examples already. Correct? I can also get the stiffness matrix for a plane frame. In a plane frame, what I have to do is 2, 6 were already here, 2 and 6 were already here, 8 and 12 were already here for a plane beam. I have to only add 1 and 7, right? I don't have to introduce any twisting, and I don't have to introduce any movement in out of the plane direction. We are only looking at the movements in the plane of the board or plane of your screen. So movement in 1 direction, movement in 2 direction, and rotation in 6 direction. Okay. that also produces deformations in two directions. Right? So this time we are bringing in 1 and 7 and all the corresponding coupled terms. If you take that separately, this is how that stiffness matrix looks like. So these terms are still belonging to the plane beam problem. In addition, we are adding these terms of axial behavior. Okay, so we have only introduced the terms of axial behavior, and you can see that axial terms are not coupled with any other term. Axial terms are completely uncoupled. So that's pretty straightforward. We just have to add these two rows, 1 and 7, and these two columns, 1 and 7. Okay, to the plane beam problem. Fine. Any challenges, any issues here? This is all very mechanical, very methodical. There is no additional mystery here. So that's why I'm kind of not waiting too much on each slide. I'm moving forward. If you have questions, please do ask. Okay, so anybody has a question? Go ahead, please. If you have a question, you can ask. I can wait for 2 minutes. Okay. Fine. So far, all the problems that we had done were regarding plane beams, right? So if you are dealing with the plane beam problem, so a plane beam is typically restrained or is restricted to move only in the perpendicular direction. So movement in this direction and a rotation in this direction, or to keep it positive sign in this direction. Only these movements are allowed. Axial deformations are not allowed. And that's why when we deal with plane beams, we only go in a single direction. We cannot bring in members at a different angle, because then it won't be a plane beam, because then it will be introducing some axial behavior. So if we have to solve this kind of a problem, right, and if this beam deforms in such a way, okay, this cannot be purely flexural deformation for this beam also. Any movement like this of this beam will introduce axial deformations for this beam. Okay, so this has to be a plane frame problem. It cannot be a plane beam problem anymore. Agreed? So this is a plane frame problem. Now we have to incorporate the 1, 2, and 6 degrees of freedom. That is 3 degrees of freedom at each joint. That means my stiffness matrix for each member will be what size? What will be the size of the stiffness matrix?
12 by 2.
Plane frame, not 12 by 12 for each member.
6 by 6.
6 by 6, right? 1, 2, 6, 7, 8, 12. Okay, so this will be the stiffness matrix. Agreed? Fine. So for member 1, let's try to write the stiffness matrix for member 1, and then we will try to write the stiffness matrix for member 2. However, we have to be careful that the way we have developed the stiffness matrix, first we will call one node as J, the other node as K. Here we will calling this node, that is this node in this member, as J, and this node as K. Then our one direction, that is also the X direction, will be oriented along J to K. Okay, that is already fixed. And then accordingly we have to develop the stiffness, assign the coordinates for 2 and 3, that is Y and Z. Okay, so what we will do is, since it's a plane frame, all these 2 and 3 we will keep in the same plane. Let's not rotate unnecessarily. And the cross-section properties are given, let's say EI in both directions. Okay, so EI is given as constant, so that I'm assuming that it has only, plus we have to deal only with one EI, that is in this plane, 2, 6 plane, right? So that EI is constant. So we will deal only in this plane. We will not unnecessarily define 2 and 6 in out of the plane direction. Okay, because that is the EI that we have to deal with. All right, so our 1, 2, and 6, and 7, 8, and 12 are pretty clearly known to us. Here 1, 2, and 6, 7, 8, and 12 are also known to us. So we can develop the stiffness matrix in this plane and likewise in this member. But those stiffness matrices will be aligned, or will be aligned according to these degrees of freedom. So what is happening here is that this one here is actually going in this direction, right? This one. But this 7 here is actually going in this direction. So the challenge will be, after I'm done developing a stiffness matrix for this member and this member, there will be one stiffness matrix for this member. Then there will be one stiffness matrix for the other member. The challenge here will be that I cannot simply assemble them like we did before. Because earlier, when we had two beams aligned in the same direction, the 1 degree of freedom for this beam, we were not dealing with 1. We were dealing with 1 here and 2 here. And then 3 here and 4 here. So this was 1, 2, 3, 4. Then again 1, 2. Sorry, 1, 2 and 3, 4. This is how it was, right? So the 3 and 4 here were exactly aligned with 1 and 2. We were able to do a simple overlap of the stiffness matrices like this. You remember that? We had done this overlap, combined overlap, and these terms were all 0. Agreed? That we won't be able to do now. Why? Because the 1 here is not perfectly aligned with 7 here. Okay. So we have to do something called transformation, or rotational transformation. So before we go into rotational transformation, at least let us develop the stiffness matrices for member 1 and member 2. This is member 1. This is member 2. What is the length of member 1? It has length L. Member 2 has a length of square root of
5 by 4 L.
9 by 16 L square plus L square. How much will that be? 4.
5 by 4. 5 by 4.
5 by 4, is it? Okay. Yeah, correct. So the length of this member is 5 by 4L. That is 1.2L, 1.25L. Fine. So the stiffness matrix, we have already seen how to develop that. This is the axial term, EA by L minus EA by L. I'm calling it AX, that is in the X direction. It does not have to be mentioned explicitly. 12 EI by L cube, 6 EI by L square. All these terms you are familiar with. So we develop the stiffness matrix for SM1, that is first member. But this is in this coordinate system. That is, this is X, this is, sorry, this is X. However, for member 2, the stiffness matrix will be developed in such a way so that the X direction is this one. And this will be the stiffness matrix. Now you can see the terms are very similar except for this L value changing. Okay, so instead of L, now we will use 1.25L. The rest of it is exactly the same. So every time wherever we were using L here, we will be using 1.25L now. Okay, but assembly is a challenge, right? Because they are not aligned together. So when I do a unit movement in J direction, sorry, when I do a unit movement in one direction here, it does not also mean a unit movement in 7 direction here. So I cannot simply assemble this term with this term. Because a unit movement in one direction here basically means some movement in 7 direction and some movement in 8 direction. Correct? Right. So this can be broken as some movement in 7 direction and some movement in 8 direction. It cannot be simply assembled. That thing brings us to some transformation concepts. Okay, shall we discuss that today? Shall we discuss that today? Transformation. Okay, so the transformation of vectors, I'm sure you must have already been taught at some level. Have you guys taken any finite element courses or any level of transformation you have studied before? Transformation matrix for a vector? No. Or maybe you have a little bit, but you don't want to say it yet. You're not confident enough. So let us say we have some coordinate system. I'm calling it XS. Can you see this screen where I'm writing right now? YS.
Yes, sir.
Yes, sir.
And I'm calling it XSYS, which basically S stands for structural, but you can just one coordinate system it is. What is the direction of Z? Z is in the out of the plane direction. You can imagine the right hand rule. So X, Y, Z. So that is coming out of the board in our direction. Fine. And I have a vector called A. Okay. Vector called A. Now this vector would have two components. Correct? What will be the value of this component here? It's projection on the x-axis, right? So when it is a projection, that means this angle is 90 degree, obviously, right? That's how we define these vectors. So this A value will be equal to AXX, AYS. So this value here is and this value here is AYS. And AXS, AYS, that is in X and Y direction coordinates, it defines A. Okay, and let's say Z value is 0 or whatever the Z value is. Let it be, it has some Z value. You can call it AZS also. Okay, it has a Z value. Now the challenge is that I want to define this vector in a different coordinate system, and let me call that coordinate system as M coordinate system. So this one was S coordinate system, but I want to use M coordinate system. Okay, let me see how M is defined. So let's say M is a coordinate system which has an XM in this direction and has a YM in this direction. Fine. And the M coordinate system is created at an angle of gamma in the counterclockwise direction. So I'm calling it positive gamma from at an angle of gamma rotation about which axis are we rotating?
Z-axis.
About Z axis, right? Z axis. So if we rotate it about Z axis, what I've done is I have rotated XS and YS by a gamma angle about the Z axis, ZS. And if I have done that, the projection of this vector in the Z direction will not change, right? So my AZ at ZS value will not change. It will remain as it is because I have not rotated my Z axis. My Z axis is still in the same location. However, my X and Y have changed. Now in the new coordinate system, the same vector A, can be written as AXM, AYM, AZS or ZM. You can use either because Z is not changing. Z is still in the same location. So you can call it ZS, ZM, doesn't matter. The same value. This value would not change. But these two values would change. And how would I know that those values? We draw the projections using this color. So these are the projections on the structural coordinate system, S coordinate system, right? And that's what defined AXS and AYS values. This length from here to here was AXS. This length from here to here was AYS. Now, if I have to calculate AXM, how would I get? Which projection do I have to get? I have to get the projection of this one over the XM axis, right? And this angle will be 90 degrees. Agreed? So this value will be AXM. right? And if I take a projection in this direction, sorry, it's not a parallel. On this axis, what will this be? AYM, correct? So what do I need to do is if I know the values of AXS and AYS, I need to calculate the values of AXM and AYM. Okay, and if I can, if with the knowledge of this angle gamma, if I can do that, if I can find out the values of AXM and AYM and AZM is already known. AZM is already known. If I can find out these three values, I have done the transformation. I have found out how to define vector A uniquely. In S coordinate system, I already knew, but how to define it in M coordinate system too. If I can find out these three values. And what I know in between is that this angle gamma was used to move from S to M. So instead of me keep drawing here and making it more complex, let me refer to this pre-drawn sketch here. So just to recap again, this is the structural coordinate system XS, this is YS, this is XM, YM. It is achieved, M coordinate system is at an angle of gamma in the anti-clockwise direction from XS rotated about the Z axis. Okay, this is vector A, which is defined as AXS, AYS, or also defined as AXM and AYM. Fine. So all I want to know is how to know AXM value by using AXS, AYS, and gamma, and how to find out the value of AYM again by using AXS, AYS, and gamma. Okay. So let's do some 8th grade geometry now. Okay. And I have color coded it to help myself and to help you also. So I want to know the value of AXM. AXM is how much? Where is AXM? AXM is up to here. From here to here. That is the projection of A on the XM axis. So that is AXM. Agreed? Now AXM, if I look closely here, let me go to the previous slide. These were the projection. This projection, this additional line I have drawn, right, which is basically parallel to this line here. Okay, and this will help us out in a bit. Now, if you want to know what is this angle, can you tell me what this angle is? This angle is gamma. What is this angle?
Gamma.
This angle I don't know for sure. This one is gamma. Are you sure? How do you know? See, gamma was the angle between this line and this line. Gamma was the angle between this line and this line, right? These two lines. Now, if I draw perpendicular lines to both of these, again, the angle between them will be gamma. So this line is perpendicular to this. That is why it is parallel to this, right? Because this was also perpendicular to xn. So this line is perpendicular to this, and this line is perpendicular to this. So therefore, the angle between them will still be gamma. Agreed? If I have two lines, the angle between them is gamma. If I draw perpendicular lines, so line perpendicular to this will be this one, line perpendicular to this will be this one. The angle between them will remain gamma. Agreed? So that's why this angle is also gamma. Okay. And if this angle is gamma, what is this angle? These two lines are parallel, right? This line and this line are parallel. This is also gamma. Okay. With this knowledge, let's try to move forward. Now, I want to know what is the value of AXM from here to here. Right? So AXM is nothing but summation of let me see, I X is equal to AXS cos gamma. So AXS cos gamma will be this much, right? From here to here. That is AXS cos gamma. And this much. So AXM is nothing but a summation of this part and this part, wherein this part is nothing but AXS cos gamma. This is gamma angle, right? So AXS cos gamma, this is 90 degrees. So this part is AXS cos gamma. You are with me? Plus this part. Now, how do I know what is the value of this part? So this length is basically summation of this length and this length, which is basically a projection of this one with a projection over here, right? So this projection. So this length is how much? How much is this length? I'm drawing over it.
AYS.
AYS, sir.
Yes, sir.
Yes. And this length will be how much? Will it be related with AYS? This angle is gamma.
AYS sign.
And then this length is same as this length. Right? So I got total length of AXM. That is AXS cos gamma plus AYS sin gamma. Agreed? Similarly, I want to know what is AYM. AYM is this much. That is this much. I want to know what is this length. Correct? That is, I want to know what is this length. Okay. Do I know what is this length? Do I know this full length? And do I know this much? That is this length. What is that full length, first of all? What is this full length? It will be a projection of this one, right? AYS. This is AYS cos gamma. Is it true or not?
Yes, sir.
This is AYS. This angle is gamma. So AYS cos gamma will give me this length. Agreed? Because this angle has to be 90 degree. AYS cos gamma. I've got full length, but I don't want to include the portion. I only want this length. So I want to deduct this portion. How much is this portion? AXS. Can we calculate that from AXS?
Is
Sin gamma.
sin gamma.
AXS sin gamma. Agreed? So now with the knowledge of AXS, AYS, and gamma value, I have been able to calculate. Let me erase this. With that knowledge, I have been able to calculate the values of AXM, AYM. And AZM remains same as AZS because I'm not rotating in such a way so that the projection in the Z direction would change. Projection of this vector in the Z direction would not change. Z axis is where it was. Vector A is where it was. So its projection on Z axis would remain the same. So AZS is same as AZM in the new coordinate system. But AXM and AYM have changed. Okay. This information, these three equations can be written in matrix form. AXM, AYM, AZM, these are the three values on the left hand side are equal to coefficients will be cos gamma, sin gamma, minus sin gamma, cos gamma. Okay. And then another row I'm adding just to put 001 and then AXS, AYS, AZS. Right. You can check again. AXM is equal to AXS cos gamma, AYS sin gamma, no component from Z. AYM is equal to AXS cos gamma minus AYS sin gamma. Sorry, AYS cos gamma minus AXS sin gamma, no component of Z axis. AZM is equal to AZS. Fine. So this looks fine, right? So this will become my transformation matrix for any vector which has three components in X, Y, Z direction. So if I have any vector which has three components in one in each X, Y, and Z direction, I can transform that from S to M coordinate system by using this transformation matrix. Okay. This matrix, transformation matrix, does not transform a stiffness matrix yet, because the stiffness matrix is not really a vector. It can transform a vector from structural coordinate system to member coordinate system. And what is the relationship between structural and member coordinate systems? How are the structural and member coordinate systems related with each other? Member coordinate system is at an angle of gamma, or is achieved. Member coordinate system is achieved or arrived at by rotating the structural coordinate system by an angle of gamma about z-axis in the counterclockwise direction. Correct? So if you rotate the structural coordinate system about z-axis in the counterclockwise direction by an angle gamma, you arrive at the member coordinate system. That is the definition of, or that is the relationship between x and m. And that relationship has to be used to get this relationship between, or transformation matrix. Okay. Any questions from this one? There are no questions this time. I mean, in the last couple of lectures, I feel like some of these concepts would require a little bit of thinking. And since there are no questions coming in, I'm feeling like maybe I'm losing you guys. What is the deal? Am I going too fast or too slow? I'm stopping the recording now. We'll just do a little bit of discussion.